Yeah, so last time what we did was we looked at the normal modes of vibration, and we said the normal modes are basically some fundamental vibration modes, fundamental patterns of atomic motion with which we can explain the sum total of the molecular motion or the individual atomic motion of molecule. So as I said, it does not mean that the water is going at some time this, and sometimes this, and sometimes this. So it's doing all three at the same time. And what you essentially will be seeing is a very complicated motion. But you'll know that that complicated motion can actually be resolved into the linear combination of these three fundamental modes. And that's basically what we mean by normal modes. And how many normal modes does a molecule have? 3n minus 6. This is non-linear. 3n minus 5 is linear. And we know that. We also sort of laid some ground rules as to how to analyze these vibrations. We said all those vibrations above 1000 wave numbers, 1000 to let's say about 4000 wave numbers, we call them as the functional modes. So essentially that means that if I have 400 wave numbers, okay, and 4000 wave numbers out here, let's say this is 1000. This region is essentially something which has to do with the functional groups in the molecule, and irrespective of which molecule that functional group is, it always shows up in the same place, nearly the same place, not exactly the same place, but nearly the same place, independent of what happens elsewhere. So if you have a carbonyl group in a molecule, whether it's an aldehyde or a ketone or an ester or an amine, it doesn't matter. It will show up somewhere near 1700. But there might be small changes from 1700 for various reasons. For example, if I have an amine, and compare that with, let us say, with acetone, the point I'm driving home is that this part of the molecule doesn't really seem to be doing much when it comes to what this fellow does. So this C double bond O is always going to be oscillating at a frequency roughly around 1700 wave numbers. And the moment I see a peak near about 1700 wave numbers, you always jump up and say, no, look, I know a molecule has a carbonyl group in that. But there will be small changes which you must be able to sort out. For example, this carbonyl group is somewhat different from this carbonyl group for a simple reason. I have this lone pair, and therefore I can have something of this sort of a resonance. And what does it do to the bond order of the carbonyl? It makes it somewhat less. We have done this resonance, actually it's a resonance in which we say this is n pi star type molecular orbital order. So this pi bond actually has electrons now moving into a pi star sort of an orbital, and therefore the bond order of carbonyl here will be somewhat lower. It won't be 2, as in this case, 1.8, 1.85, thereabouts, meaning it's smaller. And as the bond order decreases, what happens to your force constant? It should drop because the bond is less strong. And therefore, while if this shows up at 1700 wave numbers, you would expect this not at 1700 but somewhat lower, maybe 1680, 1660 and so on. So if you don't see it at 1700 but you see it at somewhat lower frequencies, then you know that that's a double bond, carbonyl bond, that's actually in conjugation with something else. Or you could have something like this. And this would again lead to a lowering of the bond order. And therefore, these are things that you must watch out for. So it's not the question of seeing something at 1700 and saying that it is a carbonyl feature. Seeing something at 1700 and then seeing whether it is lower or higher, and then taking a call on whether this carbonyl group is actually in resonance with a lone pair or a double bond and so on. And that's something that one can do. The point I'm therefore making is that between 1000 wave numbers and 4000 wave numbers, you have these subtle changes maybe as far as the functional groups are concerned, but what you're really looking at is a gross assignment of what functional groups the molecules might have. But when you get here, these are vibrations, low frequency vibrations, which can't be really attributed to a functional group per se, but they are sort of many parts of the molecule are jiggling around, and you call them as skeletal modes. So you might have this moving, the hydrogen here moving, rocking, and then this color will be expanding and so on. It's a large collection of various motions. And you call that as a skeletal mode. And the nice thing about skeletal mode, the bad thing about skeletal mode, they're too complicated. You can't put your finger on a peak and say this is C double bond O. You can't put a finger on a peak and say this is C double bond C and so on. But what the skeleton mode does is, because of its complexity, it becomes rather unique. So if I have a molecule and I want to find out whether that molecule is molecule A, all I have to do is to record a spectrum of molecule A, take my unknown, record the spectrum of this compound, and then compare not so much in these regions, but compare in this region and see what happens. If there is a bang-on overlap, it's quite likely that I am looking at the same molecule, and therefore molecular comparisons can be made with this region of the spectrum, and therefore this region of the spectrum is also called as the fingerprint region. We know that the fingerprints are rather unique from people to people, and if you have the mark of your fingerprint, you can actually identify it with something very similar. If I have these features over here, the very nature of the spectral features in that region actually tells me what compound it is that I'm really looking at. It's extremely hard to analyze and say what these modes are really, but they're extremely useful because they're so complex, they're rather unique. Each molecule will have its own fingerprint spectrum in that region, which you can actually use to be able to characterize. The whole course is about characterization, and this is one very neat way of characterizing. And as I said yesterday, if somebody gave you a compound A and said, can you tell me if this unknown is molecule A? Sure. All you have to do is take molecule A, which you know is molecule A, record a spectrum, and compare the fingerprint region. Fingerprint region matches, and you know that you're very likely looking at the same molecule. If it doesn't match, you know for sure you're not looking at the same molecule. You're sort of much more sure in that case. But in the first case, they match, you say, well, it's most likely this, because you have to reserve the possibility that there could be something else that is very similar, and you are not in a position to distinguish the very fine differences between them. But if spectral features are different, then of course you know that you're looking at two different systems. So, yes?
So in this region from 4000 to 1000, we are looking at the
functional groups.
Yeah, functional groups. And from 1000 to 400, we are having for the whole molecule.
That's
So
correct.
the whole molecule is vibrating means what is, in what sense is it different from the functional group vibrations? Does it is giving in that region?
Yeah. See, the whole molecule actually, when you, I didn't think this laptop came from somewhere else. If you look at the benzene, or if you look at, again, maybe the next time I'll show you this. When you look at the low frequency modes, actually what the low frequency mode does is, supposing I have a molecule, let's take this. In the low frequency region, what you might peaks over here, what will happen is, they're not just due to one group. The NH might be rocking, at the same time the CH might be backing. So it's a combination of all of these that gives me one feature out here. Then there might be another feature out here, which might be because of a torsional mode out here, and this whole thing bending back and forth. So it's a combination. Now this combination is very unique. These features are very unique for a given molecule. If I go to this color, it will not have the same structure that I would see, because the internal combinations of these vibration patterns are not going to be the same.
So in that region, we are getting the whole combination.
We are getting, see, it is not the entire vibrational system, because all these functional features, they're still out here. So this very strong carbonyl structure that is still going to come at 1700. But what this region does is actually a combination of various low frequency modes that the molecule has. And that combination is unique. This molecule will have a certain pattern out here, which is not going to be the same as this. In fact, it will not even be the same as acetamide. So that's the reason why they say that this feature out here is absolutely, which is a combination of very low frequency atomic motions of these molecules, is unique from molecule to molecule. So formamide and acetamide would probably have, formamide and acetamide would have very similar carbonyl features, but very different skeletal features. And therefore, I can actually look at the skeletal features and tell you whether I'm looking at acetamide or formamide. But I cannot look at the C double bond O feature for these two molecules and say which is which, because they both would come maybe around 1680. And therefore, using this information, I cannot tell you what the molecule is. But using this information, I can tell you I'm looking at a carbonyl containing compound. That much I can tell you. But to use the fingerprint region, you have to be posed a question that is this compound A? Because if I never told you anything, I just gave you this and said, tell me what this molecule is, it's very hard because how many molecules are you going to be looking at to see whether there's a pattern out here? Because today you have softwares that have entire data banks with them. And once you have recorded a spectrum, if you say, now look, give me possibilities, it will go and compare this region that you have recorded for the unknown compound with all the database it has for various compounds, and then come back and tell you, well, the possibilities are there, there were 5 hits, it could be any one of these 5. And then you have to use your judgment and say, well, of these 5, I think it's most likely this compound or the other compound and so on. It will not be very easy if you are posed a question, here's this compound, tell me if this compound is A or B. Then I can always record the spectrum of A or B and compare the fingerprint region. And if the fingerprint region matches for either of them, then I know I have a good possibility that it is either of them. If it doesn't match with either of them, then I know this compound is not A or B, it's something else. So the fingerprinting issues become very, very sort of simpler. If you are posed a question, can you tell me if this compound is A or B? Then is this compound naphthalene? Is this compound beta naphthol? It becomes easier because all you have to do is to record a spectrum of the compound that is being sought for and then see whether your unknown compound matches with this other compound in the region of the skeletal or the fingerprint.
So can we say in this way that the effect of motion of atoms on other atoms in the same molecule is seen in a more pronounced way in the skeletal region than in this region?
There's not much effect of atoms. What I'm saying is that there's a certain pattern of vibration for these low frequency molecules. Yeah, and that pattern is very unique for molecule to molecule.
So that is because of the composition of the molecule?
That's correct. It's because of the relative orientations of the eye. In fact, 2 conformations, for example, will have very different fingerprint regions. And you can actually tell which is which. So it's the relative orientation of the atom, the nature of the atoms that you have, and these put together will give you rather unique features in this region so that you will be able to figure out whether the compound you have in question is a given compound or not. This will not give you that information, but this region, functional group region, will always tell you very quickly as to what compound it is or what function group it is that you have. This is extremely useful for organic chemists, as I said the other day. If I get you a carbonyl compound, I can reduce it to give me an alcohol. And if you want to know the reduction is complete or not, all you have to do is take out and record the sample after a certain period of time, record an infrared spectrum, and see whether you have a carbonyl group or not. If the carbon group is gone and you don't see it, then I know my reaction has gone to completion. I don't have to worry about these fingerprint regions because I know what molecule it is and I'm preparing. All I want to know is whether the reaction has gone to completion. And to do that, all I'm looking for is to take this carbonyl feature in this case and just keep following the intensity of the carbonyl feature. As the reduction progresses, this intensity will keep dropping. And if the reaction has gone to completion, the carbon feature is completely gone. And I know my reaction is done and therefore stop my reaction at that point in time. So if you're following a reaction, you probably want to follow the functional region. If you want to identify a compound, you probably want to look at the skeletal region or the fingerprint region. So the 2 regions have very different roles to play, very different utilities in the way one could handle it. What I will probably do in the next couple of days is get up some spectra for you, compile some list of spectra and pass it on to you. And then what you should really be doing is looking at the spectra and see whether you can make predictions of what the molecule might be. In terms of functional groups, I'm not going to ask you what the, very rarely in infrared spectroscopy, one will be able to look at the compound and say that this compound is really this. Very often in infrared spectrum, we look at it and say, oh, this is a carbon compound, or this is a phosphate, or this is a amine, and so on. So that you must be in a position to figure out. So I'll give you some spectrum, and you need to look at that and see how you can analyze it. As I said, what I will do is also give you some problems based on things that we have already done. But then next week, one of the days we will have a tutorial, and that tutorial, I will give you another set of problems based on what I gave you as homework. you will have to work that out in class and then pass it on to me. So that you actually, I'm trying to ensure that you really go through all the problems and do it once. That's quite essential. So we will do that. So hopefully by about Saturday or so, I will mail you a bunch of defining both problems as well as spectrum. And please do them. So in the tutorials, I will give you another set which you can work on. Okay. What I will do now is to tell you something about the method by which you record IR spectra. We already have done it, so I won't spend too much time on that. What are the different methods? You did it by liquid, right? Liquid, and how do you do the liquid? There are many ways to do the liquid. One way is simply take potassium bromide window and smear the liquid onto it. Put it on the path of the beam actually goes right through it, and that's called the transmission mode. And in the transmission mode, you have the window, the light comes through, and what you have done is applied a small amount of the liquid and smeared it. If the liquid has low vapor pressure, or it's sort of little viscous, it's actually good because you smear it and it will stay. But I don't know whether you ever tried to record the spectrum of acetone. You will never succeed because by the time you put it around, it's gone because it's very volatile, and therefore you can't get an acetone spectrum this way because there's so much surface area that you're really showing for the molecule that it will keep vaporizing. Therefore, that's not it. But then if I gave you ethylene glycol or compounds such as those, they'll be quite easily doable with the system. This is a transmission mode where you have I naught here, and what goes through is I, and of course all the frequencies are here because we're using an FT instrument, Fourier transform instrument, and we saw early on. And what do you do in a Fourier transform instrument? You put all the frequencies in one shot, collect the data, and then you do a Fourier transformation and get information on various frequency components. You are not recording in spectrum frequency after frequency, which is what you would have done in the UV visible spectrometer. In this machine, all frequencies hit the molecule at the same time. Molecule absorbs whatever it wants to absorb at all these frequencies. And what you then see is the sum total of these intensities falling on the detector. But then by some other ingenious methods, you take this information and Fourier transform that. You get your frequency components, and then you plot intensity as a function of frequency that has been absorbed. And that's basically your infrared spectrum, which is what exactly you would have got had you taken light, dispersed it, and looked at it frequency after frequency. That's called the dispersion method. This is called the Fourier transform method. So the UV visible spectrometer basically works on a dispersion technique. The Fourier transform method works on the interference method. When you have spectrum recorded by looking at all the frequencies in one shot and then sorting them out using a Fourier transform algorithm. This is one way. What's the other way? If I had a solid, what would you do? Just make a powder of it and put KBR into it and record the spectrum using the KBR edit. Why do you want to use KBR? Yeah, it's IR transfer. But why not just take the sample and make a pellet of it straight away? Why did you put KBR in it and then do all this? If I give you benzoic acid, just take benzoic acid, put it into a pellet press. At 4 tons, everybody will form a pellet mostly. So you have a nice thick pellet of benzoic acid, put it there and record a spectrum. Why did we do that way? Why are we taking this benzoic acid, putting it in KBR, powdering it? What a mess. Pardon? Yeah, if you took a benzoic acid powder and made a pellet of it, the pellet has to be at least a millimeter thick. If it is less than that, it will keep breaking. You can't even handle it. It has to be about a millimeter thick. Millimeter thick benzoic acid will let no light go through it. And therefore, you have to dilute it. So you have to dilute it in something that is transparent to IR. And that's the reason why you take benzoic acid, put it in KBR, and then do your pelletizing. The nice thing about KBR is that it's transparent to IR. So in fact, it's transparent to IR up to about 400 wave numbers, 350 wave numbers. So 350 to about, I think, 7,000 of course, it's fine, there's no problem, it's just transparent right through. And therefore, it's a good enough material for recording IR spectra. The nice thing about KBR is also that if you take a powder, put it into a pellet, it makes beautiful pellets. Actually, it sort of melts under pressure, and then you remove the pressure, it again solidifies, giving you a nice glassy pellet. I don't know how many of you got glassy pellets, but if you really make the pellet very well, if you got used to it, if you practice enough, then you will actually see that you can make really good glassy pellets. But I'm very sure that the first time around that you made it, you probably got opaque, with islands of white things here, there, and so on. That really means that you probably took a little bit too much of sample, or you did not mix it very well, or you did not grind it very well, or you did not pelletize it long enough under proper pressure. But these are things that you sort of learn over a period of time, and eventually one will be able to make nice glassy pellets. If you don't get glassy pellets after doing all these things, then of course there's a very simple answer, which would be the answer. Maybe the caviar has probably moisture in it. And caviar, mind you, is quite hygroscopic. So if you don't handle it carefully, and that's the reason I don't know whether you were told, at least when I used to handle the lamp, just to keep yelling all the time, please close the caviar immediately and put it into the desiccator. Don't leave it outside. Because very often you open the bottle, take your samples, make a pellet, leave the bottle open, and go home. And this was very merrily absorbing all the moisture over a period of time. And the next time somebody comes to make a pellet, it will always be white. Because you have actually dumped enough moisture into it by its very innate capability to absorb moisture. So you've got to handle it very carefully. So what we essentially have to do very often is take the caviar, heat it, so that it drives the moisture away. And then this powder is then very carefully stored inside a desiccator. So if you're really doing experiments where you want to be absolutely careful about what you're doing, this is the way to do it. You take caviar, you heat it at about 110 degrees or so for about half an hour, close it, put it in desiccator, after it is cooled, use that. That will be really nice. And you will essentially get extremely good pellets. That's the other method, wherein you use the caviar. So liquid and a pellet, caviar pellets. What's the third one? ATR, that's the attenuated total reflection. And what did you do in attenuated total reflection? You have this little strip of zinc selenide window, zinc selenium compound, zinc selenide window. And again, why zinc selenide? Zinc selenide is transparent to iron. But excepting that, unlike caviar, which goes from 7,000 to about 350, zinc selenide will only go from about 7,000 or so to about 650. Actually, to cut off at 650. Beyond that, it starts to absorb. So it has its own absorption, and therefore it's no use beyond 650. But very often people use zinc selenide for various reasons instead of potassium bromide. You can have the cell that you used over here, there's a little window that was made of potassium bromide, and you used your liquid was actually smeared onto this, and then you recorded it. But very often people, instead of using a caviar window, they will also use a zinc selenide window, a nice 1-inch diameter window made of zinc selenide. If the transmission cuts off at 650, obviously you think potassium bromide is better because I can see a larger window. It's actually cutting off at 650, but very often you will find that people will actually use zinc selenide in many, many cases, particularly if you are in the industry, you want to use zinc selenide very often. Why? Why do you think that's? In spite of the fact I'm losing intensity beyond 600, I can't record peaks beyond 600. 600 to 400, I'm losing information, but I would still want to use zinc selenide. The reason being, potassium bromide, as I just told you a little while ago, is very susceptible to moisture. It can be attacked by moisture and very soon it will fall. And once it falls, there's a way to polish it, and then you have to keep polishing it. And if by some chance somebody made a mistake and used aqueous solutions of water-containing sample to record a spectrum, your caviar is gone because it will immediately dissolve. Something which one of my friends in college did. He was told, here was a sodium chloride cell. Just wash it and bring it back. For a moment he forgot that the sodium chloride is extremely soluble in water. He just took water and started washing it. And there in front of his eyes, the window just went away. Of course, he went away from the lab and didn't come back for 3 days because he knew what this guy was going to tell. So that happens. But then zinc selenide, on the other hand, is absolutely resistant to moisture. You can drop it in a bucket of water and use soap and everything to clean it and bring it back. It's good. Nothing happens to it. So the nice thing about zinc selenide is its extreme resistance to water, and therefore nothing would happen. In the industry, for example, if they know that the compound they are really monitoring has got features at 1000 or 1200 or 2000, why have a material that is susceptible to moisture when I don't need that information in that region? I would rather use zinc selenide and be absolutely sure about the credibility or the stability of my window, and that's the reason why it is used. In ATR we use zinc selenide, but that's for a more technical reason. It is not the